Section 4.6 relates relative velocity and relative acceleration. And what this really comes down to is reference frames, right? When we talk about a relative velocity of two things, we can talk about viewing the reference frame as each point of view. So first, let's consider two people on a moving sidewalk at an airport. They're both standing on the moving sidewalk. All right. So let's call this person A, this person C. We're going to have person B out here standing on the ground. So person A observes person C standing still. Right, they're both on the moving sidewalk, neither one of them's walking, and they observe them to just be standing there. What does person B observe? Person B observes person C zooming by, right, at whatever the speed of the walkway is. Let's say it's moving at 2 meters per second. So person B observes person C moving at 2 meters per second. All right, who's right? They're both right. So what this comes down to is just frame of reference. And you could even get into a talk about inertial reference frames. We're not really ready to talk about that. Neither of these frames are accelerating, so all of our physics would hold in either reference frame. All right, so that's kind of the most basic example we could get. So the next thing I want to talk about is like a current in a river. Right, kind of same idea, right? We're talking about the person's speed on the moving sidewalk. We can talk about a boat moving in a river, and we could do this in 1 or 2 dimensions, right? You could be paddling your canoe upstream or downstream with the current flowing down. All right, so that we have a 1-dimensional problem. Or we could have our river and we could be trying to paddle our canoe across. And the straightforward way to do this is just vector addition. So if we were to look at how person B observes person A in our previous example, well, person B observed person C moving at 2 meters per second, and person A observed person C moving at 0 meters per second. So we can shift between those reference frames by just adding or subtracting 2 meters per second to the right. So we can connect, just transitive property there, basically, person A to person B. What does person A observe of person B, right? they observe person B moving at 2 meters per second to the left, right? Because from their point of view, where they're moving at 2 meters per second relative to person B, they have the opposite point of view. Now, if we talk about the speed of the canoe in still water, then that would be the reference frame relative to the water. Right, that's why we denote it as still water, right? So the water's not moving. What happens when we put it in the water and we want to talk about the speed of the canoe relative to the bank? What does that look like? Right, well, if the canoe is moving in one direction with its paddling along at whatever its speed is in still water, then we also have to include the current, right? Because the water itself is moving relative to the bank. So, simple example, right? Let's say the V of the current is 3 meters per second. And V of the canoe in still water is 5 meters per second. And you're trying to paddle across the river to get to this dock. You know, which way do you have to paddle? If I aim exactly at the dock, well, I'm going to drift downstream, right? So I'll be here, and then here, and then here. I'm not going to make it straight across, right? So I have to actually aim my canoe upstream. Oops. So that the sum of the velocities is straight across. Right, and I didn't put vectors on my blue one. This is if we're pointed straight across, right? These are velocity vectors for the canoe itself based on the paddling. Right? And these are the headings. What more do I want to say about this? We didn't talk about relative acceleration yet. So I think an interesting place to talk about this would be the International Space Station. Right. We know that when you're in Earth orbit, you feel weightless. You're actually not. We'll talk about this directly from some gravity calculations later. But what actually makes you seem weightless is that the space station that you're in and you are both experiencing the same acceleration due to gravity. And that means that in your shared reference frame, there's no difference in acceleration. When we're on the Earth, the Earth is not accelerating the ground down, right? It's in equilibrium. And if we are above it, then we accelerate down to the ground. Imagine that you're in a elevator and the cable snaps and you're now falling at the same rate as the elevator. You appear to be weightless inside the confines of the elevator. If you didn't know that the elevator was falling, you would just think that you were weightless. So that's one example of relative acceleration. We could look at other things as well. I just think that's a very interesting example. All right.